right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Let's do that. And yeah, let's jump into it. Okay, so exciting stuff to talk about today. We are going to actually solve the rate problem. But before that, we have someone's trying to get in here. We have some examples to finish up from continuity. So we had that one last example, and there was this random example that I made up off the top of my head in my last class. So I decided I might as well tell you guys about it. So we'll just do these two examples very quickly because you're already even quizzed on this stuff. So you already know enough to do this, I think. Also, speaking of the quiz, so I haven't put your grades into Gradescope yet, but that's because I know that we were a little bit behind schedule because of that class we missed. So you did not actually know how to do every single question on the quiz. So there were about 2, maybe 3 problems where I would say you wouldn't know. And so what I want to do is I want to actually review the quizzes again to make sure to pick out those problems and count those as bonus problems instead. So while your quiz was auto-graded, I still want to go through it and just make sure that I'm fairly counting against you what I should be counting against you. So I didn't just mindlessly upload the grades. I still have to go through and do that. So when that's done, I'll do that a little bit today, maybe right after class, in fact, and I'll publish your grades so you'll see how you did. That being said, let's actually jump into it. So yeah, all right. So yeah, for the most part, just gonna go through these very quickly because there's nothing really new to talk about by way of instruction. It's just us applying the concepts we know about continuity. So yeah. Okay, so we were asked to find where this is continuous, so we know what to do. Essentially, you notice that potential problem. Something to prop up the tablet here. Is that a weird angle for me? So we say that potential problem. At x equals -2, that is clear because of how this thing is broken up. Then you look individually at the functions and you'd realize otherwise you're kind of fine. The first one is a rational function, the one in the top line. That's defined and continuous as long as our denominator is not 0, which it is not because it's only that definition for x not equals -2. So we made that statement. If x not equals to -2, we're fine. So now we just want to focus about at x equals -2. So now, first thing I want to check is, does the function have a definition at -2? And it does. It is 1. 2. Now I want to know about the limit as x approaches -2 of the function. So what limit is that? Well, I have to go up here and I have to see which one the limit would apply to. Now remember, limits do not care about what is actually going on at the point. So I would not look at that line. That's not the line I want to look at. I want to look at this line because that's what the limit cares about. It cares about getting close to -2. So it cares about being a little bit to the right or a little bit to the left. So I don't actually want to be at -2 when I'm taking the limit. I don't care. So the limit is actually that function, limit of that function. So this is x squared plus 5x plus 6 over x plus 2. Now, once we know that's the limit we want to take, we go into limit strategies mode that Jhevon told us about last time. And I think this guy factors into that. Yeah, that looks about right. these guys cancel. And here we end up with the limit as x approaches -2 of x plus 3. And now I can actually plug in -2. I get 1. And so now 3, I just do my check. I know that the limit as x approaches -2 of my function was 1. And hey, that is actually equal to the value of the function at that point. So ding, 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 you say f is continuous at x equals -2 specifically. And this means, of course, you don't have to claim it, but since we know that if x not equals -2, we're continuous, I can conclude that f is continuous everywhere. So yeah, this function is continuous, and pretty much a very similar thing happened to the last example. So the idea was this function actually behaved like x equals, like y equals x plus 3 most of the time, except when we were at -2. So there was a hole here. This passed through 3. So this was your f of x for x not equal to -2. Then at -2, your function definition filled in the value. And it filled that in at a level of 1. And so now there was a hole, but we actually filled it in the right spot. We can actually just draw right through -2 without lifting our pencil off the page, because it's now continuous everywhere. In fact, this function is now equivalent mathematically to y equals x plus 3. There's no difference between the two now. Before there was a difference. Like if I didn't have this part, then this would not be the same as y equals x plus 3. It will be y equals x plus 3 with a hole in it. But by me adding this part, I have now made it, it's essentially the same as y equals x plus 3. I've made it continuous. Y equals x plus 3 is a polynomial, it's continuous. Let's look at this one. So this was ones that I mentioned to you guys that would be there, that sometimes I would put other variables, but they represent numbers. So they're not meant to be taken as an X or a Y, but you need to find the variables that get something to work out. So some of the students in the other class asked me about another example problem, and I just gave this off the top of my head. So hey, I just decided I'll go through it with you guys as well. So here is a function. We are given the definition, but we don't know everything. There's an A and a B in it. And we want to find the values of A and B that would make F continuous everywhere. I was really doing it off the top of my head. I didn't even realize I didn't write the word make. Or justify why no such A and B exists. So of course, you'd realize here, so how you'd go about this is, again, you identify potential problems. Now, obviously, x equals 2 is a problem because I am one thing. This wasn't also typo. because I'm one thing to the left of 2, and I'm another thing to the right of 2, and I'm another thing at 2. So obviously x equals 2, all sorts of craziness is going on there. So that's definitely something I want to look at more closely. I would realize that if x not equal to, we have polynomials. So we're fine. So of course, x equals 2 is an issue because the definition of the function changes around there. But now when I look at the function itself, if I look at each line, the first one is a minus x, the second one is 0, the next one is x plus b. These are all polynomials. These all work as far as they work everywhere. So really, as long as I'm not at 2, everything is actually fine. So now really focusing on 2 is going to be the issue. So at x equals 2. Now, this is slightly different because I'm not asking you to find where it's continuous. I'm asking you to find values that force it to be continuous. So here, this comes down to whether you know the definition. You'd have to say something like, we want the limit as x approaches 2 of f of x to be equal to f of 2, right? So we still have to check these 3 things, right? That f of 2 is defined, the limit exists, and the limit equals the value of the function. We're still going through that check. So now, f of 2 equals, go up. I'm told in the definition that f of 2 is equal to 0. So that's 0. That's easy. Okay, 2. I want to know what the limit as x approaches 2 of f of x is. Maybe someone can quickly tell me here, what is that? How would you go about finding that? Limit as we approach 2, how would you do it? Where is everybody? Is Madeline the only one here?
Wouldn't it be the limit of a minus x?
Why would you say that?
Because like in the one before, we didn't care about hold on, let me scroll up. In the example before, we didn't care about 1 because it already was defined as x equals -2. So since we want to find as we approach, for a minus x, x is less than 2.
Yeah. So is that all our limit would care about?
No, it would also care about x plus b as well.
Yeah. So how would you deal with that?
Would we just find both of them?
How would we do that? So you're right in that we're going to ignore this line because x equals 2. But obviously, I can't just take one of the others because for one, it's only less than 2, and for the other, it's greater than 2. And the limit actually wants both sides to work out, right?
Yeah, so would we do like the limit of x as x approaches to negative for one, and then the limit of x approaches to positive for the other one?
Right, but say left and right. don't say positive and negative. Okay. So yeah, so here you'd realize that well, I can't really just say the limit all at once because it breaks into 2 parts, right? It breaks into, well, there's a different thing coming from the left as there is coming from the right. So now you'd have to notice that on either side of 2, the thing is defined differently. So I need to make sure that I'm doing that carefully. So on the left, it's a minus x. And on the right, it's a plus x plus b. So this one is going to be, well, a minus 2. And this one is going to be 2 plus b, right? And for the limit to exist, which we want it to exist. Remember, the goal is to force this thing to be continuous. we need, what do you need?
Wouldn't we need them to both be the same outcome, I'm gonna
Right.
say it as, to
You
equal
need
each
them
other?
both. You need them both to be the same, right?
Yeah.
So we know that. Okay. So we know that the function is defined at the point to be 0. We also know that these two expressions needs to be the same. So the third thing we need to do is to make sure the answers in 1 and 2 are the same, right? So what that essentially now means is that I need to make sure that the answer from part 1, which is 0, is equal to the answers from part 2, which is a minus 2, which also needs to be equal to 2 plus b. So this tells me that I need a minus 2 to be equal to 0, and at the same time, I need 2 plus b to be equal to 0. This, of course, means that a must be 2, and b must be minus 2. And that's your answer. Okay. So for this function, to make sure that this is actually continuous, I would need a to be 2 and b to be minus 2, and then it would work. So it would actually look like a so on the left it would look like 2 minus x. Is it? Where are we? I need a to be 2 and b to be minus 2. And we're on the left of 2. Okay, so on the left, so we are at 2 here. One part is going to be this going down here. This is the f of x equals 2 minus x part. That's going to go through 2 and 2. And then there is the other part, which is actually going to be going up. This is f of x equals minus 2 plus x. So you know that that would have extended and hit this at minus 2 for the y-intercept, but we don't care because that's not the side that it cares about. And then finally, at 2, we fill in the hole at 0. Okay, so it kind of looks like a weird absolute value, right? It's actually equivalent to an absolute value. It's equivalent to the absolute value of x minus 2 in absolute values. That's exactly the graph that you would get. So to force this guy to be continuous, you end up forcing him to behave like the absolute value of x minus 2. Yeah, so those are some examples. But now I want to move on to the main thing of today's class, attacking the rate problem. So I can tell you right now what we are going to do, but I think I don't know, maybe it's me, maybe I'm just a little bit of a nerd, but I've always liked how we figured out this problem. So I'm actually going to tell you guys how we figured it out. Yeah, at the end of this, I'm going to actually give you the answer to this question that calculus came up with. So remember I mentioned to you that calculus is about two main things. We want to solve the rate problem and we want to solve the area problem. And we invented things called the derivative and the integral to solve each of these problems. 300 years ago, we realized that, hey, these are actually the same problems, just two different sides of the same coin. We're actually all working on the same thing. Let's all come together, and boom, calculus happened, right? So calculus is kind of the study of these two areas, but with the understanding that we can use our knowledge in one area to help us with our knowledge in the other area. And then a lot of nice applications just fall out of that right away. I mean, once we can talk about how much space something takes up and how fast something is moving, you can actually tell a lot of other things as well, as we'll see. And you can tell a lot more things than we will actually cover in this class, but we'll see some cool applications in this class as well. But we are going to attack the error problem. Now remember, hopefully you remember what the error problem actually was. And what I want to do is to give you a motivating example to kind of show you where the idea came from. Maybe I want to cut this. Okay. So here's the motivating example. Okay. So we're going to figure out how to actually do it in a very idealistic scenario, which is what math is good for actually, right? You have these real world problems. The world is complicated. We don't know what the hell is going on. So what you do is you abstract, right? That's what the power of abstraction. You just like get rid of all the fluff, get rid of everything, pretend we're in the simplest situation possible in the perfect universe. What would the answer have to be? And then we take that and we translate to the real world, right? So now that's what we're going to do with this essentially. We want to know, how would we go about measuring the speed of something just like as an idea, right? So suppose we have an object, it's traveling, and you want to measure how fast it's moving. Again, let's make very basic ideal assumptions. The object is moving at constant speed. It's not speeding up, it's not slowing down, it's just, right? Just make it easy on ourselves and just say, let's figure out how to make it, if something is just moving and I know it's not, it's just like very steady, could I measure how fast it's moving? So it turns out, yes, we can. And we can do that by tracking its distance, the distance that it's traveled over some time. So something is moving, I don't know how fast. What I can do is I can track it in the following way. So that's what we're going to do now. We are going to graph the distance the object traveled over time. So measuring this object, and I had nothing to do with my day, so I'm literally watching this thing for 3 hours, right? And in 3 hours, it traveled 150 miles. So here's how that went down. So here, you'll notice that if I put, say, time on this axis, distance on this axis, and let's say here I write hours and distance in miles, I'm like, okay, I start my stopwatch at time equals 0 and my distance is 0, right? So this is the initial point of measurement, right? So it's at 0, 0, right? So the object is moving and there comes a point where it passes this point and my stopwatch goes off and then I start watching it now, right? So this is time 0, distance 0. Reminds me of a YouTuber though, which is, yeah, it's a good YouTuber though. So now we're just watching it, right? And here's what we notice. After watching it for 3 hours, we noticed that it ended up covering a distance of 150 miles. So there came a point where the object was over here, right? So the distance was that, right? So when time was 3, it works better when you make this sound with your mouth. Right? So when time was 3, it covered 150 miles. Now this thing is moving steady, which means there was no time where it will cover a vast distance in a very short period of time, and then a small distance in a very long period of time. So the curve cannot be crazy. If it's moving at constant speed, the curve would have to be a straight line, right? Because it's not speeding up or slowing down. It's not covering a lot of distance in a little time or a very small distance in a lot of time, right? Has to be a straight line if it's moving at constant speed. So that is the graph of distance versus time, right? And now here, I am going to lead you into a question. He's leading the witness, Your Honor. What is the slope of this graph? What is the slope of this graph that I just drew?
Would it be 50?
It'd be 50. How do you get that? Well, there are a couple ways. You realize that the slope, well, that's the change in the y over the change in the x, right? So it's like y2 minus y1 over x2 minus x1. And we already know where our x1, y1 is 0, 0. And we know that our x2, y2 is 3, 150. You can also just look at the fact that the rise was 150 and the run was 3, rise over run, right? So this guy is the same as rise over run, etc. But in either case, you're going to realize that the rise was 150 and the run was 3. So this gave you a slope of 50. Awesome. So 50 is the answer to part B. Okay, not so bad. Where is he going with this? All right, so let's go to part C. Now, this is the important part. I want you to interpret the answer to B. So you just told me about the slope. We got that number 50. What, 50 what? 50 pesos, $50? Like what is this 50 about? Interpret the number that you got here.
Couldn't we say 50 miles per hour?
You could say 50 miles per hour, right? Because here, the y-axis was tracking miles and the x-axis was tracking hours. In fact, if I were to put units, I know that the slope would be equal to 150 miles over 50, over 3 hours, right? And I can reduce this to 50 miles over 1 hour, right? In other words, we call this in everyday life 50 miles per hour. In other words, the slope is the speed. It's like how fast the object was actually moving, which is interesting, right? So 50 miles per hour, that's how fast it was moving.
What is the PE multiple?
Right? So I started out having no idea how to measure how fast this object was moving, but by tracking some other variables, I tracked 2 variables. One was independent, right? So time was just going, I can't control it. And one was dependent. At a certain time, the object is at a certain distance, right? So there was an independent variable and dependent variable. There's another variable that I really care about, which was speed, but I didn't have access to that. But I used these other 2 variables to get access to it. And I got access to it via slope. Quite interesting. So now, yeah, in the event that we have an object moving at constant speed, I know how to figure out how fast it's moving. Just watch it for a while and track what distance it covered over that time. Divide one by the other, that's how fast you were moving, okay? So, which is interesting. Okay, so that's the simple idealistic case. I know how to track an object, how to figure out how fast something is moving, provided it's moving at constant speed. However, look around you. How many things move at constant speed? How many things are always traveling at the same speed all the time? Almost nothing, right? So yeah, the question is, okay, can we generalize this? So this is what math people do. They come up with a simple idealized version of the problem. They solve the simple problem and they're like, can we apply this to a more complicated situation? And it turns out, unfortunately, the answer is no. So thanks for dropping by, I guess. See you guys next time. No, I'm kidding. No, we do know. Yes, we can, right? Yes, we can. God, I should have missed opportunity for a Barack Obama meme right here. Okay, so yeah, we can actually generalize this. Now the question is how? How do we do it, Captain? Okay, so that's what we're going to figure out now. Because if we can generalize this to any object moving at any random speed it wants to, at any time it wants to, dude, that is solving the rate problem. So again, let's start out a little bit simpler. So I am going to just talk about an object that's moving according to this random graph that I have here. Okay, so this one is not moving at constant speed. As you can see, it's curved. Right? Now, I'm not saying every object is going to have a curve like this when you track distance over time, but this is just an example, right? So here's a different object. It's not a straight line anymore. So what do we do now? So obviously the speed isn't always the same. So now you can note speed isn't always the same. In fact, this is an object that it's actually speeding up. Like in the beginning, it was moving slower than it was moving at the end. You'll notice that it took a long time here to cover almost no distance, but then in a short time here, it went from here to up here, right? Which means it traveled a far distance, which means it actually moved faster towards the end than in the beginning. That's not very important though. Right? I just want to point out that the fact that it's not a straight line, you can figure out that that means not constant speed. They're actually equivalent, right? Which means what we care about now, what we care about then, is something called instantaneous rate of change. Or speed, right? In other words, the question is different now because there's no one answer. It's not like this object where someone tells me how fast it's moving, I can say 50. I can't do that here because even if I say 50, it's not always going to be 50. It's going to change. In fact, it's going to be speeding up. The moment I say 50, it's not going to be moving at 50 anymore. So now the question has to be different. Now we have to make it more peculiar. I would have to define a point that I care about. So how fast is it moving here, right now, in this instant? Right? Because asking how fast it's moving in general isn't really a question that makes sense anymore with a numerical answer, right? So instead, what you can do is you can just figure out how fast it's moving in the moment that we're looking at it, right? That's essentially what we want to do, right? So we're watching this object move. It's not moving at constant speed, but we're like, how fast is it now? How fast is it now? How fast is it now? Is it faster or slower than it was, right? Like you want to be able to track it, right? How fast it's moving, right? This is the idea of the rate problem, right? So how fast are we moving? So we want to apply the above idea. i.e., slope is equivalent to speed. Speed isn't the right word. More accurately, what we call velocity in some sense. So yeah, now I realize, well, if I were to measure the slope, that would tell me how fast it's moving. But how do you measure the slope of a curve?
With a tangent line.
With a tangent line. And yeah, Sarah totally just stole my thunder just now. Like that's going to ultimately be the answer, but we don't know that yet. We're before calculus happened, right? We're trying to figure this out. Okay, so how do you actually measure the slope of a curve? It's not a line. We can't use y2 minus y1 over x2 minus x1. It's just it's wavy. Like how do you do that? Where's that thing? Okay, here's the graph again. how do you actually, what's going on? No, why can't I grab this? Is there something wrong with the thing? Yeah, I don't know what's going on with that guy. But he does not want to be grabbed. He does not want to be touched. Okay, does not have my consent. Can I grab this one? Okay. That one allowed me to grab him somehow. Okay, so now, lasso. Okay, let's copy this guy because he doesn't mind being copied. Okay, so yeah, how do we measure the slope of a curve? The answer, surprisingly, is to think. Yeah, the answer, surprisingly, is to think like a flat earther. that's surprisingly the answer. Right. Math teaches us so many lessons. Sometimes you can have someone that's so wrong, but at the same time, you shouldn't just completely disregard them and ignore everyone you don't disagree with. Because sometimes, in some contexts, thinking out of the box can actually help us get somewhere. Because here's the thing, it's curved, sure, but it's curved on the scale that we're looking. You see, if we were to zoom in, the curve won't look so curvy, right? Like, it's why the Earth looks flat to us, even though it's not, right? Because of the scale we're at, right? If you zoom in far enough, even curved things look flat, right? So the idea is, okay, it's a curve now and I don't know how to deal with it. So what do? Well, zoom in. The more you zoom in, the flatter it would look, hopefully. And so the idea is now the curve almost looks like a straight line. But which straight line? Right? If I can find the line, I can find the slope. Let's make it up. So I go in here and I'm like, all right, if I zoom in far enough, my curve starts to look very flat, starts to look like a line. So what I'm going to do is whatever line it starts to look like, let's superimpose that on the picture, right? So this guy is the line it starts to look like. The more we zoom in. We'll call this a tangent line. Thanks, Sarah, for ruining the surprise. Next time, please shout out spoiler alert. Okay, so the idea is if I zoom in, it starts to look flat. It starts to look like a line. What line? What's the equation of that line that it starts to look like? Because if I know the equation of the line it starts to look like, I'd be able to tell the slope. So the idea is, okay, let's just put the line in there, pretend we know the line. How would we actually figure out what its equation is to get the slope, right? So that's what we're doing. This line is called a tangent line. Tangent means to touch. The idea was it touches it locally in one point, but that's actually technically incorrect. Tangent lines don't have to touch a curve only in one point locally, but that's another story. This is where the name comes from. It's not completely mathematically accurate. So that's the idea. If we can find the slope of the tangent line, we can find the slope of the curve. So how do we do that? Right? Well, of immediate concern is that I literally only have 1 point. I have 1 coordinate. We only have 1 point. Every schoolboy knows we need 2 points to find a slope. Right? You need the x2 and the y2 to go along with the x1 and the y1, right? You can't just have an x1 and a y1. How are you going to get a slope from that? Like, you don't know what the rise over run is. You're at the point. So again, and this is again something that math people do, is that we pretend we have the answer before we have the answer, and then we just kind of see what that answer would have to look like. Also a technique that's out there. This is also good in life. It's called reverse engineering. So sometimes you want to achieve a goal. You just imagine, what would it be like to have that goal, and what would have to come before that in order for me to get to that goal? And then you kind of build up from there. So that's what we're going to do. So let's pretend we had another point. So here, back in this situation, we go in and we're like, all right, so a little better. So there is the point we care about. And here is another random point we made up. And what I'm going to do is I'm actually going to connect those with a line. And so this is the line that connects the 2 points. Now, this is a line that we have seen before. Anyone remember what this line is called? A line that connects 2 points on a function like this? We looked at it when we were studying average rate of change. It's called a secant line, right? So there's that. So now we have this situation. So we have our second point, which means we know the slope of this line. So the slope of the secant, we saw that before. That was this guy. That was the difference quotient, right? So if this guy here, if this were x and this were x plus h, and this were f of x, this was f of x plus h, are the y corresponding y values, we can measure the slope of the secant line there. Not the slope of the line that we want, though. We want the slope of the tangent line. So essentially, I want the slope of the line that passes through that one point. Right? So I have this. I have a line connecting these two guys. And right here, I have a line that I care about. So this is my tangent line. And this is my secant line. The tangent line is the one I care about. Right? So now the question is, how do we actually get it? So here is the genius idea. Well, we need 2 points to find the slope at this point. We have a second point, but it's too far away to be of use. That will tell me the average rate of change. That will tell me the average speed over some very long time interval. I don't want the average speed at some very long time interval. I want it at a very small time interval. So in other words, we are in a situation where I can tell you how fast this thing was moving over some long period of time, but I want to know in an instant, how fast is it moving right now? So the idea is take the period of time and make it smaller. So we know that the period of time between these two measurements is h. So the idea is if I can make h smaller, that would work. So there's a point where I want to know the slope at, I don't, but there's another point where I know on average how fast it's moving. What about if I move that point super close to this one? So then it's like I have 2 points in the place where I had 1 point, and then I can use my formula for 2 points in the case of having 1 point. It's like, it's genius. That's how we'll do it. What we'll do is we'll make the h smaller. So what we can do then is we'll have this situation where I'll have the part right here where this is the line that I care about, but then I would have a bunch of lines. So yeah, I didn't make the noise in my mouth, that's why. So here, but if I move the point closer, then that becomes this. I really should start doing that. And if I move it here, then it goes. Then if I move it here, it goes. Then if I move it here, it goes. What do you notice? The secant lines start getting closer to the tangent lines. Right? So I know about secant lines. I know how to find their slope. I don't want the secant line. I want the tangent line. So what do? We use what we know how to do to figure out how to do something we don't know how to do. The idea is if I just squeeze the time interval smaller, the secant line will actually become the tangent line, right? And so now the question is, all right, so here's a point I care about called x. And here was some farther point, x plus h, and I wanted to get this point to move closer to that one. In other words, I wanted this distance here to get smaller. Now, I don't want that distance to go to 0 because then I'm in the situation where I'd only have 1 point and I can't do that. So I want this distance between these 2 points to become super, super close to 0. So close that it's effectively 1 point, but I really want to be able to think of it as 2 separate points. So I don't really want the distance to be 0, but I want it to get super, super duper close to 0. So now we're like, do we have a mathematical mechanism for actually doing that, getting super close to something without actually being there? What would even do that? What is that, right? Do you mean just plug in the, no, plugging in the number means you're at the point. We need something to get super close to the point. And then you realize, well, you didn't realize this, but this is the problem. And so here is like, well, let's just invent something. So they go, you pause, you go invent the limit, go invent limits, right? Because you need to know, you can't just say, oh, just make it 1 point close to the other. You have to have some mathematical machinery to say you can do that. The limit provided this machinery. You're like, what does it mean to actually get close to something, right? What does it really mean? The limit tells you what that really means. So you want this point to get close to that point. How do I do that? You go invent limits and then you come back. right? And so what we can do is we want h to approach 0. We can accomplish this with limits. So in other words, the slope of the tangent line is really just the limit as h approaches 0 of the slope of the secant line. So it turns out that I know how to measure the slope of the secant line. That's the difference quotient. If I make the difference quotient, the denominator of the difference quotient approach 0, I would end up with the slope of the tangent line, right? And so that's it, we did it. Now, you probably don't appreciate the importance of what we just derived. Many years of study actually went into this, and we went over it in like, I don't know, 10 or 15 minutes or so. But yeah, this is an important limit. Muy importante. And because it's super important, we give it, yeah, I love how Sarah's like yawning on me. This is super important, it's the best thing ever. Okay, if you say so, John. So yeah, this is an important limit, right? We give it a name. We call it the derivative. Okay, now, well, more appropriately, we do this. This limit solves the rate problem. Guess we'll give it a name. We'll call it the derivative. Yeah! Then you walk out the frame, right? Like, okay, so you have to say it very like cool, like, because it's actually a really big deal. Turns out this solves the rate problem. Want to know how fast something is moving in general? Find that limit. That limit will tell you. How fast is it moving at this point? Find that limit, it'll tell you. How fast is it moving at this point? Find that limit, it'll tell you. As long as that limit exists, which of course, because we use limits, we have to worry about it existing or not. As long as that limit exists, it tells you the answer. It will tell you how fast you're moving. And that's the solution to the rate problem. This is the calculus solution to the rate problem. Find this limit, it tells you how fast you're moving, right? So this leads to our main definition. Let f of x be a function. The derivative of f of x with respect to x denoted by f prime of x is given by So I believe there was a quiz problem where I asked you to define the derivative, and you had to pick out from the answer choices which it was, and this would have been the answer, provided this limit exists. So word on notation here. F prime, as it's called, this is Newton's prime notation. It's read F prime of x, right? So we call it F prime of x, or F prime. So that was the notation that Newton came up with when he was developing his cohesive theory of calculus. Turns out in Germany, around the same time, but it came out a little bit later, another mathematician kind of came to the same answer for the rate problem. It was a mathematician by the name of Leibniz. And believe it or not, his formulation was actually a lot nicer than Newton's. Newton's got the job done, but this other guy had very nice notation. He had the theory written up a lot nicer. Newton was actually not concerned about the math itself. Newton was actually concerned about a problem in physics, and he invented calculus to solve this problem in physics, right? That's the guy we're talking about. That's Newton, right? You ask him one question, he invents a whole area of math so that he can come and answer your question, but then answer any other general questions you might have about this scenario, right? So he wanted to know about motions of planets in the solar system, so he invented calculus to answer questions about that and predict, where would Jupiter be at this point in time in the year, right? So invented calculus to figure that out. This other mathematician called Leibniz, which was more into the math side of things, so he developed it more for the math theory, also developed something. He came up with his own notation. So there's other common notation. It's called the Leibniz notation. So if y equals f of x, Leibniz notation looks like this. He actually started out thinking of it as delta y over delta x, but that's really the slope of the secant line. He actually moved that to say, well, d, right? So he went from pretty much like Greek letters to English letters. That's what he did. So this was the slope of secant. Rise over run, right? A very familiar idea. This is what he called the slope of tangent. He just changed the alphabet on you, right? So he called it dy dx is the derivative. And he read it the way I just said it. He read dy dx, right? So you don't already say dy divided by dx or dy over dx. Everyone says dy dx, and we know what you're talking about. And that's very important, right? That's why I'm telling you how it's read. It's very important not to know just what you're talking about, but to also sound like you know what you're talking about. So when you're talking to people, you should say dy dx. This person probably knows what they're talking about, right? So, when you have that dy and then there's a slash and then there's a dx, like I'm not going to listen to this person. They probably don't know what they're talking about, right? It's read dy dx. Okay. So that's the notation. Let's do an example. Do I have any? I actually don't remember if I typed out the example already. I feel like I did. Let me see. Ah, yes, I did. Okay. All right. So typed it out in the over here. So now that we have that, let's do some examples. Right. So these examples are just to get you used to the definition. We'll talk about, applications and so on and so forth later on. But I'm going to get through one example. We're going to explore it a little bit, and then maybe we'll do a couple of these examples if we have time, and then I'll let you guys go. But yeah, so. I'll have to make that bigger some other time. So hard to format on this thing. Okay, so here is the example. So I want you to use the definition of the derivative to find the derivative of this function, x squared. Very nice function. It's simple enough as a first example, but complicated enough to not just be super trivial. It's not a straight line where you can just tell me, oh, well, that's the slope right there, isn't it? Right? It's one step above that, right? And I want us to use our answer to find the equation of the tangent line. Well, that's what we're going to do. So here, A. So I know that f of x equals x squared. This means that f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. We need to know this definition, so every time we're going to use it, we're going to write it down until we know it like the back of our hands and we can recite it in our sleep. That is the definition of the derivative. Limit as h approaches 0 of f of x plus h minus f of x over h. Literally on day one of class, we looked at how to do the part, compute this without the limit part, right? So hopefully we don't have to go over that again. So f of x plus h means everywhere you see x, you replace it with x plus h. Do not distribute powers across sums. This is x squared plus 2xh plus h squared minus x squared. These guys die. Do not cancel across sums. We would factor out the common h. Now we can cancel. Those guys die. To x plus h. And now I can actually plug in the h. Notice that I could not plug in h equals 0 because it was undefined. I would divide by 0. But remember our limit strategies. If I can't plug in the number, try to simplify so I could plug in the number. So that's what I did. I simplified so I could plug in the number. And I can. And the answer is 2x. So it turns out if f of x equals x squared, then f prime of x equals 2x. Huh, interesting. What does it actually mean for the derivative to be 2x? Isn't that just another function? Well, remember, x squared is the kind of curve that's not always moving at the same speed. So if you want to know what speed it's moving at, you need to know at what point in time we're talking about. So what you want to think of this as is it's a formula that tells you what the speed is at the point you care about. So if someone says, okay, I'm on the graph x squared, how fast am I moving when x equals 2? Well, you're moving at 4 units per unit time. How fast when x equals 3? 6. How fast when x equals 9? 18. How fast when x equals 0? 0. How fast when x equals minus 1? 2, right? Notice that at any point where you ask me how fast we're moving, I can tell you because I know the derivative. I can answer your question right away. The rate problem is solved in general. Tell me what point you care about, I'll tell you how fast you're moving, right? So that's what this gives you. This gives you a formula for the slope at any x value. I'll tell you about more interpretation of the derivative next time. Right? That's what the derivative is. That's another way to think about it. Right? So yeah. And whenever I say use the definition, this is what I mean. You have to use the limit definition, use limits and difference quotients and simplify it and stuff like that. So yeah, just a heads up, like on the test, I'm definitely going to ask you this very traditional kind of question to ask in a calculus class. It's not going to be the same function, but I'm going to ask you, well, pretty much literally the same question. I'm going to give you a random function and I'm going to say, use the definition of the derivative to find the derivative. And you have to do it this way. I'm going to tell you shortcuts for how to find the derivative a lot quicker and a lot nicer and a lot cleaner, but there are going to be times where I'm going to ask you to actually, tell me, flesh it out, show me from the definition how to find the derivative. It's just going to be a thing. And if you do the shortcut when I ask for the definition, then you're going to lose the credit. So just so you know. So this is important for you to know how to do, right? So a question like this is, it's definitely coming on test 1, so expect it. Yeah, now, so that's the derivative, 2x. So now, using your answer to part A, find the equation of the tangent line when x equals 3. So how would we go about doing that? So, well, let's see. So B. Now remember, the tangent line is just a straight line, right? It's not anything any more complicated than that. It's a straight line in a very special context, but it's just a straight line, which means I would find it the same way I would find any line, right? Need the slope and a point. Or in this case, or you can do or 2 points, but it doesn't apply here. Because I don't have 2 points. You just told me 1 point, x equals 3, right? Doesn't apply here. Right? So we're looking for a straight line, which means I just need to know a slope and a point. If you only gave me the point, I now need to know the slope. So we know the point. Do you get the point? Do you? So we know the point, or we know how to find it. When x equals 3, this means our y would be 3 squared, which equals 9. This means the point is x1, y1 equals 3, 9. So yeah, we know the point, or we know how to find it, right? You tell me the input, I can find the output, I can get the point, that's fine. How do we get the slope? Well, that's what we just figured out. The derivative is how you get the slope. So it turns out the slope at x equals 3 is f prime evaluated at 3, right? So here I would say m equals f prime of 3. I know f prime is 2x, so this is 2 times 3, so this is 6. So the slope is 6. So this means I can get my tangent line now with the point slope form. Y minus y1 equals mx minus x1. And so y minus 9 equals m, which is 6, x minus 3. So that's the line. This is what's called a point slope form. If necessary, required, you can solve for the y. So this would be y is equal to 6x. 3 6 is 18, so 18 minus 18 plus 9, it would be minus 9. And that's more like in your mx plus b form. This is called the slope intercept form. So that is the tangent line. So what have we done here? What do we learn? Okay, so just for you to kind of see what we actually did, I want you to, maybe I can use this. I want you to see what we actually did. Oh. So it's like we have y equals x squared doing its thing. There was a point of interest over here when x was 3 and our corresponding y value was 9. And what we just did was we're like, what is the tangent line here? Let's call it this guy. So that's the tangent line. And what we actually did was we actually figured out what that is. So it's like we found the equation of this line. So if I zoom in and this curve starts to look flat, it'll start to look like a straight line. Which straight line? This straight line, y equals 6x minus 9. You'll notice that from this picture, we'll know that this passes through at minus 9. So this is has equation y equals 6x minus 9. So it has slope 6, y-intercept minus 9, and that is the tangent line for this equation. And that's what we found. We found the equation of this tangent line. Now, why do we care about the tangent line? Well, the slope of the tangent line tells us how fast, if I were to imagine that this red curve was measuring distance over time of some object, it will tell me how fast the object was moving. So I'm going to leave most of these for you guys, but right now, I'll just kind of ask you. So I'm going to want you to find these guys, and we're going to do that next time before moving on to some other stuff and me telling you some other stuff about the derivative. However, the first two, you guys should kind of know what that is, I think. I'll leave the rest in the notes. But what would be the answer to the first two? Like the final answer. F of x equals c. C is a constant, right? So like y equals 5, y equals 7, y equals 13, y equals pi. What would be the derivative of such a function?
Is it 0?
It's 0, right? So this is coming up from the interpretation. Remember, the derivative is just the slope of the tangent line. If it's a constant, it's literally a horizontal line. What is the tangent line? The tangent line is itself. What is the slope of that line? Well, it's 0, right? So we kind of know this already. And it's pretty easy to see this from just by looking at it. But if you want to do this by definition, if you want to realize, does our definition tell us what the answer is? Obviously. Well, yeah, because f of x plus h would be c, f of x would be c. So I'd have the limit as h approaches 0 of 0 over h. That's 0. Makes sense. What about this one? F of x equals cx, where c is a constant. So it's like y equals 5x, y equals 7x, y equals 15x. What would be the derivative?
Is it 1?
So I had y equals, say, 15x. The derivative would be 1.
No, it would be the constant. It would be c.
It would be the constant. It would be c. Yeah. So again, you know that this, and this is coming, I'm kind of leading you into shortcuts that I'll be telling you. We'll know that things like, oh, the derivative of a constant is 0. And we won't have to always do this to know that. It'll just be something we know now. But that's kind of where I'm kind of leading into. So yeah, this will be c. And you kind of know that's obvious, but we can see this relatively quickly. Again, by the definition. This is the last one I'm going to do. So here, what it would look like is f of x plus h, you replace the x with x plus h. course, you'd expand this. Cx plus ch minus cx all over h. These guys cancel. Then you have the limit as h approaches 0 of ch over h. Now the h's cancel. Then we have a limit of a constant, which we know is just the constant. Now, we can express our answers to the previous three as follows. We can use the Leibniz notation, but we put the function beside it. So for example, we know that the derivative of x squared is 2x, right? So, and we know that the derivative of a constant is 0. I know that the derivative of a constant times x is just a constant. By the way, this means this guy would automatically mean that the derivative of x is 1, right? So these are just shorthand what we can say. So this, we would read it as the derivative. In Calc 1, we would normally leave this out, but in Calc 3, there are many independent variables, so sometimes you have to make people know which one you're talking about. The derivative of x squared is 2x, right? That's how you'd read it. d dx of x squared equals 2x means the function y equals x squared is 2x, right? And you can actually say it shortcut. So when I'm giving you rules, I'll be giving you them in shorthand like this, where you'll just know the derivative of something that looks like this is this, right? And really what happens is we went through and we did these limit calculations, but at the end of the day, we can come away with certain rules that we can take advantage of. And we will take advantage of those next time. So we'll stop there for now. Thank you for your attention. Hopefully everything was clear, but we will wrap up there unless there are any other questions. I'll leave these guys for you to try. So try to figure out the derivative by the definition for these two guys. Suppose I gave you the function 1 over x and square root of x. Those are a little more complicated. It's not obvious just by looking at them what the answer is. So these are a bit more involved. But at the end of the day, once you find these answers, I'm just going to ask you to know the answers at the end. I'll give you some generalized rules for situations like we've looked at. Okay, we will wrap up there. That is it. Hopefully you guys followed along. Thank you for your attention. I will let you guys go. Yeah, so that being said, see you guys in the next one. Ciao.